Okay, so maybe let's start. Today's webinar is at an unusual time, a bit earlier than always. And this is the reason is because the speaker is from Japan. It's already 7 in the evening in Japan. And the speaker is Ryuji Nomura from Hokkaido University. So thanks a lot for agreeing to give a webinar here. So please start whenever you're ready.
Okay. Thank you, Dima. My name is Ryuji Nomura at Hokkaido University. And first, I'd like to thank the organizer for giving me opportunity to talk about anomalous oscillation and the dripping of superfluid droplets. So first, let me show you that our experimental setup. We have a glass dewar, and in the dewar, we have a liquid helium, and we cool down this liquid by evaporation cooling and make a superfluid in a glass dewar. And we have a cup in the dewar, and we scoop this liquid in the cup. Then the liquid in the cup flow out through this film flow, and it drips from the bottom. And we observe the dripping of this pendant droplet by a high-speed camera. And our temperature was 1.6 Kelvin. And the reason that we have such kind of a film flow is due to the fact that liquid helium completely wets the wall over all kinds of the substrate. So first, let me explain this wetting. Okay, this is a definition of the contact angle. We have a solid substrate, and on the solid, we have a liquid droplet. And this angle is a contact angle, alpha. And for the superfluid, this angle alpha is 0. And that means that it completely wets the substrate. So this is called complete wetting. And this is due to the fact that interatomic interaction between helium atoms are weaker than the interaction between the helium atom and the substrate atoms. So the liquids are strongly attracted by the substrate. So and it's completely wets the wall and spreads by making this kind of thin superfluid helium. So liquid helium wets the all kinds of the substrates. So if we prepare the glass cap and if we scoop the superfluid in it, then this superfluid climbs up this wall by making a thin film against the gravity. And it flows through this thin film and it drips from the bottom. And if this liquid is viscous, we cannot expect such a film flow because this film thickness is very thin, a couple of tens of the nanometer. But this is nothing for helium because it's a superfluid. So it can go through this film and drips from the bottom. And we can observe this pendant droplet formed on the bottom of the cup. And in our case, the diameter of this cup is 30 millimeter. And we observe this pendant droplet by a high-speed camera. And we measure the length of the droplet as a function of time. And we also measure the volume of this pendant droplet. So this is the bottom line of the cup, and the droplet oscillate in this way. So we measure this length of the droplet as a function of time. This was first thing we measured. And we also measured the volume of this droplet. And because we observed only from the one side, so we assumed that the cylindrical shape for this droplet. Then from this image, we estimated the volume of the droplet as a function of time. Okay, so this is the length of the droplet and the volume of the droplet as a function of time that we measured. Here, the droplet are stretched, and this means, at this point, the droplet are pinched off, like this, pinched off. And just after the pinched off, the remaining pendant droplet on the bottom of the cup start to oscillate in this way due to the recoil of this pinch off. And around here, it's again stretched downward and pinched off at this time, and repeat this process. And what we measure is the dripping period of tau. It's the time between two pinch-offs. So we measure this dripping period tau. And during this oscillation, the volume of the droplet is increasing. It's nearly proportional to the time. And at this pinch-off, the volume suddenly decreases like this. And from this slope, we can estimate the flow rate into the droplet. So V dot we can measure during this oscillation process. We can also measure this V dot, the flow rate. Okay. So next, let me show the time evolution of the dripping. And this L is length of the droplet as a function of time. And during the dripping, just after the scooping, the liquid in the droplet decrease. And this decrease in the, just after scooping the superfluid in the cup, the amount of the liquid in the cup decrease. And this decrease result in the decrease in the flow rate. And the decrease in the flow rate result in the gradual increase of the dripping period. So let me show. So around here, the flow rate is high and it oscillates one time and drip around here. But later it oscillates twice. And around here it oscillates 3 times. So the amount of liquid decrease and the flow rate decrease and the number of the oscillation increase. So around here it's 4 times. Around here it's oscillates 5 times. Around here it's 6 times. So you can see that the timing of this dripping was completely governed by this oscillation because this oscillation amplitude is so large. Okay. This is what we measure, dripping period tau as a function of time we measured. And we also measured the flow rate V dot into the droplet. As you see, as a function of time, the flow rate into the droplet gradually decreasing like this. And due to this decrease, the dripping period increases like this. But this increase in the dripping period was not smooth. You see that step-like change. So, for example, around here, the flow rate are changing, it's decreasing. But the dripping period is keeping the same stable value. And after this flat region, it suddenly jumps to the next stable region. So the change in the dripping period is stepwise like this. And these are black dotted line are this value, 0.22 plus 0.08 times n. And the agreement with this stable region is good. And the n corresponds to the number of the oscillation. So you can see that the timing of the dripping is completely governed by the number of the oscillation. And this was plotted against the time, but next I plotted this tau against the V dot. Okay, this is a dripping period tau as a function of the flow rate V dot. I think this is a more essential plot. Do you see it also changes in step-like changes? We have a stable region and sharply changes to the upper step like this. And here is the zoom up around this region. So it has a stable period, even when the flow rate into the droplet is changing. So this flat distribution means that it has a fixed dripping period, even when the flow rate into the droplet is changing. So we observe this kind of a stable or fixed dripping period. Okay, this is a collection of the trajectory of the length of the droplet. it oscillates and it drips around here, and it oscillates and drips around here. So you see that the bunching of the trajectory like this. And around here, most of the case, it drips. And okay, lower graph is a histogram of the dripping period. So due to this bunching of the dripping, we have a peak in the distribution of the dripping period, like this, due to the bunching of this trajectory. And in this histogram, you see many peaks, and their separation between the peak is equal. So they are equally separated, like this. And these vertical lines are the value of this. And the agreement with this peak position is good. So this 0.08 corresponds to the oscillation period, and n corresponds to the number of the oscillation. So again, you see that the timing of the dripping is completely governed by the high amplitude oscillation. Okay, and this behavior of the superfluid helium is quite different from the dripping period for the water. This is a well-known example of the water dripping from a faucet, and this is a well-known example of fluid chaos, and it's taken by Kiono and others. They measure the dripping period tau as a function of the flow rate B dot for water, and this is their result. And here's a zoom up. You see that this dripping period tau is widely distributed, even when the flow rate is fixed at this rate. And this wide distribution is believed to the manifestation of the chaos for this dripping of water. So this result is very different from ours. In our case, we had a fixed flow rate. We have a fixed dripping period, even if the flow rate are changing. So it's appeared in this way. But for the water, it's appeared in this way. It has a widely distributed dripping period, even when the flow rate is fixed at this position. So this is chaos, and it's widely distributed. And the reason for this wide distribution is believed to be the oscillation of the pendant droplet of water. Okay, this is a dripping of water. And just after the dripping, the oscillation period is short. It's oscillating in a short period, and as the volume increases, the oscillation period becomes long. And this is seen also in this graph. Okay, this is just pinch off, and just after the pinch off, it oscillates in a short period. But as the liquid grew, the oscillation period becomes longer like this. So the water, the oscillation period is size dependent, and this is a normal behavior, and it's constant with this expression. This is a calculation of the oscillation frequency of the spherical free droplet. And deviation from the sphere is specified by this spherical harmonic function y, and the KL is the indices to specify that mode. So omega KL is oscillation frequency for the KL mode. And you see that R is droplet radius. So this means that the larger droplet should oscillate at lower frequency or in a longer period. So larger droplet oscillate in quite slowly in a longer oscillation period. And this is a well-known example. And this is a normal behavior for the water. But helium, it was quite different. Again, this was the same, but I put again the length of the droplet as a function of time. And this is a pinch off. After the pinch off, the pendant droplets should start to oscillate. But as you see, this oscillation period is time independent, like this. But during this oscillation, the volume of the droplet is increasing like this. So this time-independent oscillation means that the oscillation period is volume-independent. And this is quite strange behavior. And we observe the quantization of the dripping period or the discretization of the dripping period for the superfluid. And I think two things are important. One is a high amplitude oscillation. This amplitude is so high, it's comparable to the droplet size, and it's never dumps. It keeps oscillating in same amplitude because it's a superfluid, and once it starts to oscillate, it's never dump. And this is one thing important for the quantization of the dripping period. The second thing is that the anomalously size-independent oscillation. This is just a constant as a function of time, independent of this volume of the droplet. And these two things are important for the quantization of the dripping period. So again, this is oscillation of the superfluid pendant droplet. And these oscillations are anomalously size independent. And this oscillation mode can be specified as a k equal 2 and L equal 0, quadrupole oscillation mode. So I call this oscillation the anomalous 2-0 mode. It's a quadrupole oscillation with this pendant droplet. And it's oscillate in a high amplitude in a vertical direction like this. But at the same time, you see that the droplet H is also oscillating on the surface of the bottom of the cup in a horizontal direction. And this motion of the droplet H, free motion of the droplet H can only be realized in the superfluid because the surface of the cup is pre-coated by the thin superfluid layer, and it prevents any pinning of this droplet H motion. So it can freely move on the substrate. And also the zero viscosity is important for this free motion of the droplet, I think. So this kind of anomalous oscillation of the pendant droplet is very specific to the superfluid droplet, I think. So as I said, this oscillation involves the oscillation of the droplet H like this. So droplet H freely moves for the beer glass cup. And I thought that it's important for the anomalous oscillation. So I tried to pin this motion. To do so, we made a cup with a narrow column on the bottom. So we prepared this kind of narrow metal column, brass column on the bottom. And the diameter of this column was 1.5 millimeters. Then you see that during the oscillation, droplet H is successfully pinned on the corner of this column. So droplet H can be pinned by this column. By changing the bottom shape, we can change the boundary condition for the motion of the droplet. Okay, I'll show again. The droplet H is pinned at the corner of the column. And from this motion, you see that just after the pinch off, it oscillated in a shorter period. And as the liquid grew, it oscillates in a longer period. You see, it oscillates in a short period initially, and it becomes longer. I'll show it again. Initially, it's short period, and it's gradually increase the period. So you can see that in this graph too. Again, this is the length of the droplet as a function of time. And this is the pinch off. And just after the pinch off, it's oscillate in a shorter period. But eventually, the oscillation period becomes larger like this because the volume of the droplet is increasing like this. So this increase in the oscillation period is due to the increase in the oscillation period by the increase of the volume. So in this case, the oscillation period is volume dependent. So in that sense, it's a normal behavior So I call this oscillation normal to zero. So in the pinned case, the behavior becomes closer to the water, oscillation with the water. So I measure the dripping period as a function of time for the pinned case of the column of the 1.5 millimeter. And the blue dots are the flow rate. The flow rates are gradually decreasing. Even if we have a gradual change, we don't have any step-like change in dripping period tau for this case. We have one small step here, but other than this, it has a small change and it has a wide distribution. And this initial step is from the oscillation of the zero times oscillation to the 1 time oscillation. We have a small step here, but other than that, it has a continuously changing dripping period due to the decrease in the flow rate for this case. So I plot the dripping period tau as a function of the flow rate. And we have an initial small step here, but other than this, the flow rate continuously changing without any step-like change. And the distribution of the dripping period is much wider than the case without the column. So the behavior changed a lot. It depends on the geometry of the bottom shape of the cup. So in this case, it's closer to the water dripping. Okay, and this is a histogram of the dripping period, tau. And we have only few peaks in a short time scale. But other than this, we don't have any peak-like structure in this histogram. So we have no quantization or discretization in a dripping period for this dripping from the column. Okay, so let me compare two cases. And this is initial one, the cup without a column, and the anomalous to zero. And this is the later case. We have a column of 1.5 millimeter diameter. In this case, we have a normal to zero. So let me show the trajectories. So in this case, we have no pinning, and the oscillation is the anomalous to zero. And you see that bunching of trajectory. And these are the stable or fixed dripping period, even when the flow rate gradually change. And now it moves to the next stable period like this. And you see the bunching of the trajectory. But for the normal mode, we don't have such a bunching, and the dripping timing of the dripping is widely distributed. So this is a kind of a normal behavior. And in this case, the edge of the droplets are pinned. And it shows a volume-dependent oscillation. So it's normal to them. Oh, this is still moving. In this case, you see the bunching, and now around here, and it will move to the next step. So let me show that change. Yeah, it's moving to the next step. And now it started another stable dripping period practice. So these two behaved quite differently. Okay, let me skip. This is the whole collection of all the trajectory. So these two behaved quite differently. So again, I'll show the histogram to compare these two. For the bare glass cup without a column, the edge of the droplets are not pinned. They can freely move. And you see the many peaks with equal separation for the distribution of the dripping period. But for this 1.5 millimeter diameter column, the droplet edge is pinned, and you see only the few peaks in the lower. You see the few peaks in a shorter time scale, but at a longer time scale, we don't have a peak-like structure. So we have we have no quantization for the dripping period for this pinned case. Okay, I show the oscillation period tau for the non-pinned case and pinned case as a function of time. For the glass cup without a column, the oscillation period is time independent. So it's oscillating in a constant period. And I call this anomalous 2-0 mode. But for the column, it's pinned, and we have a time dependence in the oscillation period due to the volume dependence of the oscillation period. So I call this normal 2-0 mode. And these two behavior is makes a difference in the dripping period, I think. So next, let me explain our present understanding of the difference. Okay, for the pinned case, we have a size-dependent oscillation, and I called it a normal 2-0 mode. Then the oscillation period TO is somehow it's a function of the volume of the droplet, for example, like this. And the V0 is the initial volume just after the pinch off. And the V dot is a flow rate into the droplet. And it's oscillating in this way. Initially, it's oscillating in a short period, and it becomes longer, like this. And its approach to the critical volume, then in the downward phase of the oscillation, it drips. And this is a pinch off in this case. And another case, we may have a scatter in the initial volume. Then it's also oscillating this way. But the trajectory between the two is completely different because the oscillation frequency, oscillation period depend on the volume. So around here, near that critical volume, it's in a downward phase, it has a pinch off, but the timing of pinch off is different from this case because the initial volume is different. So these two trajectories are different. And this makes the difference in the timing of the dripping. So the scatter in the initial volume, delta V0, causes a scatter in the timing of the dripping, tau. And this causes no peaks in the distribution of the dripping period, tau. For the pinned case, normal case. But for the non-pinned case, in this case, oscillation frequency, oscillation is size independent. So I call this anomalous 2-0 mode. Then the oscillation period, TO, is constant. So in one case, it oscillates in this way. It oscillates in a constant period because it's volume independent. And around this critical volume, it's stretched and it's pinch off at this time, at this timing. And another time, we may have a scatter in the initial volume. But this trajectory is exactly same as this above case because it has a volume independent oscillation. So around here, it's stretched and pinched off at exactly the same timing above, exactly the same timing as this, the upper case, due to this volume independent oscillation period. So the scatter in the initial volume, delta V0, does not influence the timing of the dripping. So this causes the robust quantization of the dripping period tau for the non-pinned case, anomalous 2-0 mode case, I think. And this is my present understanding or explanation for the difference between these two cases. And until recently, I had no clear explanation why we have such an anomalous oscillation for the superfluid. But recently, I found a theory that may account for our observation of the anomalous oscillation. This theory is quite recent, 2023. And Zhang and Zhou calculated the oscillation frequency of the pendant droplet in a wide range of the contact angle alpha from 0 to 2 pi in various conditions, non-pinned case and pinned case at arbitrary K and L mode. So they can calculate the resonant frequency of the any kind of a KL, like this kind of higher mode. They can calculate. And this is their result for the non-pinned case and the pinned case. And the vertical axis lambda is a scaled resonant frequency for the 2-0 mode. Lambda is scaled. F is a real frequency, and it's scaled by this TC. TC is a capillary time. It's scaled by the capillary time. So lambda is a scaled frequency. And they calculated this lambda as a function of the BO. BO is a bond number, and it gives a ratio between the gravitational energy and the surface energy. And if the size of the droplet is large, this R is large. So gravitational effect is larger, and the bond number becomes larger. So in their calculation, most of the case, this scaled frequency monotonically decreases in most of the cases as a function of the bond number. And it becomes 0 around here. It means that the droplet is unstable and it's pinched off at this position in most of the cases. But you see the one anomalous behavior for the alpha equals 0 case. Alpha equals 0 and the non-pinned case. Only in this case, the frequency is non-monotonic. Initially it increases, and after this maximum, it starts to decrease. And this non-monotonic behavior seems to be related to our observation with the volume-independent oscillation. I don't have time to explain the detail, but this condition agree with well with our observation. Only the alpha equals 0 and the non-pinned case, the anomalous behavior show up, and it's constant with our observation. And this non-monotonic dependence on the size of the droplet is constant with the volume-independent oscillation. So this may account for our observation of the anomalous oscillation of the superfluid droplet. Okay, so anyway, we observed the robust quantization of the dripping period for the freely moving droplet edge case. And the dripping was induced by the continuous driving. It's film flow into the droplet. And the system spontaneously breaks the time translation symmetry. And the system chooses the stable dripping period by itself. And that's independent of the driving. Driving means that the flow into the cup. And my question is, can we regard this phenomena as a new type of a continuous time crystal or not? Maybe this is not a good idea, but because of course, it's not a uniform phase, it's a droplet. And I'm not quite sure that such a dripping can be regarded as a time crystal, but it really satisfies some of the requirement for the time crystal because it chooses a stable period by itself without any fine tuning. System chooses that the period by itself, and that's independent on the driving. Driving means that the flow into the droplet. So assume that it's possible to regard the phenomena as a time crystal. Then this dripping period tau corresponds to the lattice constant in the time direction of the time crystal. And the different stable value means that different stable phases of the time crystal with different lattice constant. And their stabilities are shown as a function of the driving. So this can be regarded as a kind of a phase diagram for the time crystal. But I'm not quite sure such an interpretation is a good one. So I appreciate any comment on such an interpretation of the phenomena. Okay. So far, I explained the dripping from the bottom of a spherical cup and also from the narrow column with the diameter of the 1.5 millimeter. Then next, let me show the dripping from a wide column of the diameter is 5 millimeter. So this column has a wider diameter, 5 millimeter. Then in this case, we observe that this kind of a new motion of the droplet. It oscillates in a horizontal direction like this. It's pinch off and move to right, left, right, left, something like this. And I think this horizontal motion of the droplet should be the so-called Noether mode. And the Noether mode is corresponds to the mode with K and L is a 1-1. So it's a 1-1 mode. So it's like a dipole oscillation, but on a flat surface, it has a translational symmetry. So it is a zero frequency mode because we don't have any pinning for this motion because it's a superfluid. So if the surface is infinitely large, it should keep moving. But we have a corner of the flat region. So at the corner, that breaks the translational symmetry and the droplets are reflected at the corner. So it moves back and forth like this. And this kind of motion was theoretically predicted, but has never been observed in a classical fluid. Never observed in a classical field because in a classical field, they have a significant pinning. The droplet edge is easily pinned on the surface and it cannot freely move. But this is superfluid. And as I said, that the surface is pre-coated by the superfluid thin layer and it prevents any pinning of the droplet edge. So it can freely move. So on this flat surface, it has a translational symmetry and it keeps moving. And this is very specific for the superfluid droplet motion, I think. Okay, this is at lower flow rate. So it oscillated several times. Next, let me show at a higher flow rate. It moves in this way. It's alternatively pinch off at right and left. And in between, we have a Noether mode. I show it again. Drips and Noether mode and pinch off, Noether mode and pinch off and Noether mode. This is at the higher flow rate. Okay. So I analyzed this motion of the droplet. So we measure the horizontal position x of the droplet as a function of time. So it's oscillating this way. X is a horizontal position. Around here, it's pinched off. Then move to the left, right, left, right. So we analyze this horizontal motion of the droplet, x. Okay, this is the plot of the horizontal position of the droplet, x, as a function of time. And it's oscillating in this way. And this place, 2.5 millimeter, this means that it's the center of the column because it has a 5 millimeter diameter. So this is the center position. And I took the derivative of this data at this point. So from this derivative, we can estimate the horizontal velocity of the droplet, px. Now this is a plot of about px as a function of time. So the droplet slows down like this. This is the velocity, it slows down. And I also measure the volume of the droplet like this. And multiply this bx and b. Then this bx times v should be proportional to the momentum of the droplet. And as you see, it has a constant, nearly constant value. So this means that the initial momentum of the droplet is conserved during this oscillation. Now this supports that the observed motion of the droplet is really the Noether mode, because the Noether mode is due to the translational symmetry of the systems. So it should keep the initial moment like this. And next, I'll show the motion of the direction. I'm interested in this because how the droplet motion, horizontal droplet motion is induced is very interesting. So this PX is a pinch of position. And this arrow indicates that the direction of the following droplet motion. So this means that if the droplet is pinched off around the right corner, the next direction of the droplet motion is to the left. And if the droplet is pinched off around the left corner, then the following motion of the droplet is to the right. So this means that the Noether mode was excited by the asymmetric recoil after, okay, Noether mode was excited by the asymmetric recoil by the corner after the pinch off. So after the pinch off, the droplet has a recoil from the corner, and it's the initial drive. And after this initial drive, the droplet keeps the initial momentum, and it moves in this way. So that's my interpretation, how the droplet motion is induced on the horizontal plane. And we also observed that when the droplet was pinched off around the middle of the column, we don't observe the significant motion of the droplet. Let me show it. This is the pinch off around the corner. Then the amplitude of the oscillation is higher. But if the droplet is pinched off around the middle of this column, we don't see the significant motion of the droplet. It nearly stays around the center. And this is in between. We have intermediate oscillation. So depending on the pinch off position, the initial momentum of the droplet is determined. And if the initial momentum is small enough, it stays at this position. But if its initial momentum is higher, it's oscillating this way. So this kind of the variety of motion also supports that the observed motion of this droplet is due to the Noether. This is another support for our interpretation of the observation was Noether. Okay. Okay, this is my last slide. This is summary. On the bottom of a spherical cup, the dripping period was robustly quantized, even when the input flow rate was gradually changing. And the superfluid droplets oscillated significantly, and that leads to the quantization of the dripping period and the suppression of the chaos. And the droplet H freely moved, and the oscillation period was independent of the droplet volume. And I call this anomalous Oscillation. And my question is that can we regard this phenomenon as a new type of continuous time crystal or not? And on a narrow column, the oscillation period was dependent on the droplet size, and the droplet H was not pinned. And I call this a normal Oscillation. And in this case, dripping period was not well quantized. And on a wide column, we observed a Noether mode, and that was due to the translational symmetry of this flat surface. Okay, that's it. Thank you for your attention.
Well, thank you very much, Ryuji. So, does anyone have any questions? Unmute yourselves. Yeah, meanwhile, so I'll ask a question. So you've measured, I think all your data was at 1.6 kelvins. So there's still a significant amount of the normal component in the superfluid. So do you think it affects this motion?
Yes. Okay, the damping of it's not my experiment, but the damping of the droplet was observed for the levitated free superfluid particle in this temperature range, even in the presence of the normal component. And that Q is really high, even with a normal component for the free droplet. It oscillates a couple of 100 times, even in the presence even in the presence of the normal component. It's still a high Q for the free droplet. But in this pendant droplet, in the presence of the wall, I don't know, but we don't see any sign of the damping. So I think the effect of normal component may be negligible in this temperature at 1.6 Kelvin, I think.
Mm-hmm. And also, I guess there's a sizable saturated vapor pressure.
Yeah.
So it's not moving in vacuum. That seems to be negligible as well.
Yeah, it oscillates, but it's not many times oscillation. It's not 1,000 times. It's just less than 10 times. And I think it's still negligible. Just the tens of the oscillation. So damping is negligible for this case in the presence of the normal component and in the presence of the vapor. And at the higher temperature, we tried to do something, but the droplet oscillation dumps, I couldn't make a good observation. So so far I just made a measurement only at this our lowest temperature for the glass tube experiment.
Okay. Any more questions? Anyone?
Yes, could I ask a question, please? First of all, thank you very much for an absolutely fascinating talk.
Thank you.
I also wonder, though, maybe you've answered this already and I somehow missed it. Is the film evaporating? Because you're pumping the whole system, aren't you?
Yeah.
Does that have any effect?
Yeah. Okay. In the end of the experiment, we observed that the droplets are hung on the bottom and it disappears in a couple of, I don't know, couple of, maybe 5 seconds, it disappears. So we have a significant effect of that evaporation, but yeah, I'm not quite sure how it's important because, yeah, maybe important, but I don't know how it's working for our observation. But in our case, we observed that the oscillation in the range of a couple of seconds.
Yes.
And during that time, that we have a keep flowing into the droplet by the film flow. So I think it's compensating, but I don't think it's really completely negligible or not. I'm not quite sure.
But there's no big effect anyway.
No, not big.
Okay, thank you.
Another question? So yeah, I have a question about your Noether mode measurements. So, well, in principle, you're filming from just one side, and the column is it square or what's the?
Yeah, bottom shape is
round.
Yeah, it's cylindrical. So I said in this case we don't see that significant motion, but we only observed from one side. So I'm not quite sure that this is really staying in the middle of the column, or it moves along the side of the observation. I cannot distinguish between these two. But anyway, we observe that the different amplitude in the horizon in this right and left direction.
Okay. So it looks like the droplet kind of when it's collides with a corner, then it seems to reflect exactly backwards. So I'm just thinking.
Our observation is like this. Okay. Assume
So
that it's moving to this way, and if this edge hits the corner, it stops. But this another edge of the droplet seems to be slightly moving. So it moves, and this side stops, and this side seems to be slightly moving. Then the center of the mass slightly decreases. So it has a distortion, and this distortion is released by the reflection to the other side. So it's like a bouncing ball on the wall. If we use throw the ball and it's distorted, and this elastic energy is released by the reflection. I think similar things are happening. This side of the droplet reaches the corner, and this side still moves a little bit, and it makes the distortion of the droplet and stores the surface energy or elastic energy, and it releases, and that's the reason for the reflection.
Yeah, well, yeah, this is a really fantastic observation. So, does anyone have more questions? If not, then thank you, Ryuji, again. It was a really interesting talk. And so we'll have another webinar next week in normal time at 4 p.m. British time. And the speaker is going to be Michaelis Jaka from Sicily, I think. And we'll shortly post the advert for that talk. So, well, thanks everyone for attending the webinar, and it will definitely appear on YouTube pretty soon. So those who could not attend in person, so they will be able to watch it in the recording of it. Well, thank you very much.
Yeah, thank you, Dima, for the invitation. It was quite my good pleasure, and it's a nice experience. So thank you.
Yeah, well, thank you very much.